we've got another reaction which reacts very much in the same way. So again, I'm going to start with, this time I'm going to start with something else. I'm going to start with propanone, or propene. Okay. And essentially what happens is this, you've got your HBr. HBr is naturally polar because bromine is more electronegative, so it's going to pull electrons towards itself. So this is going to get a negative dipole and this has a positive dipole. And just like before, the double bond attacks the hydrogen because it's got a positive dipole. So I go from the double bond to the hydrogen. And just like before, the single bond from here goes to the bromine. I use a curly arrow to show that. But now we've got two possible choices. Whereas before we had two bromines, it doesn't matter which carbon the bromine attached to, because the other bromine would just attach to the other one. So it's equivalent. But now it makes a difference which carbon my hydrogen attaches to. And if I draw that out, hopefully you'll be able to see that. So what we could have is the hydrogen attaching to this carbon. Or what we could have is the hydrogen attaching to this carbon. Okay, we need a bit more space. And you're going to end up with your Br minus in both cases. With your lone pair. So depending on which carbon the hydrogen bonds to, depends on which one of these you get. And then just like in the last reaction, your bromine, since it's a nucleophile, will attack the carbon and make a bond of it. So we're going to end up with one of these two things. Either we'll end up with that, with the bromine attached to this side, or we'll end up with this, with the bromine attached to that side. And can you see how these are two completely different molecules? Here, the bromine's attached to the first carbon, so this is one bromopropane. Whereas here, the bromine's attached to the second carbon, so this is two bromopropane. So it really does make a difference which way round you do it. If ever you've got a symmetrical molecule, for example ethene, it makes no difference, because no matter which way they bond, you're going to end up with the same thing. But if you've got a non-symmetrical one, you really have to think about what you're going to get, and you could get either one of these. Okay? So that's our two curly arrow mechanisms. If you learn one, the other one is absolutely identical. So if you learn one, you've learned the other one. And there's two other reactions we need to know. Thankfully, you don't need to know the curly arrows for them. You really need to know the conditions needed for it. And they're as follows. Okay, so we can have our ethene and we can react it with water. And the conditions needed for this are a high temperature and pressure, and we also need a catalyst just to speed it up and get it going, and the one we use is a phosphoric acid catalyst. Now, the way this reaction works is like super mega ridiculously complicated because it involves bonding to the catalyst. But if I was to simplify it, you could explain it like this. The double bond gets broken, so I'm left with that molecule. An OH from here bonds to one carbon, and the other H bonds to the other carbon. Now, this is like your hydrogen bromide. Because you've got the H bond into one and the OH bond into the other, if I had a non-symmetrical molecule, I would end up with two different products, depending on which carbon my OH bonded to. So just be aware you can get two different products for this reaction as well as the HBr one. And these are the three conditions. Definitely remember these. Yeah, it's a really easy, like 1 or 2 mark question for them to ask that. And the final reaction we need to know. So you look at that. Yep. So this is an alcohol. The final reaction we need to know is the reaction of an alkene with hydrogen gas. And for this, we use a nickel catalyst. And for some reason, we need to know a specific temperature of 150 degrees C. And it works in roughly the same way. It's very complicated, but you can simplify it like this. You break the double bond, and each of the hydrogens attaches to the carbon. And that's that. So because you're adding the same thing to each carbon, you can only ever get one product. Because it doesn't matter which way round they're added, you end up with the same thing. So that's your 4 different reactions of alkenes, and that's definitely worth remembering, unless you like being homeless.